All right, hopefully you actually took a second and digested what you learned in part 1. We're going to talk about part 2. Sections 3 and 4. This is where you get into the rocket problems, start doing some serious math problems that are advanced and actually multiple steps. So there we go. This is where we ended up last slide. We find x and y of everything that's projectiles that are launched. So in this case, we've got a zookeeper with a tranquilizer dart gun that is 10 meters from the light pole. The light pole is 5 meters high. The tip of her gun is 1 meters above the ground. Same moment, the dart travels at, so here we go. Biggest thing, first, you've got to draw a diagram. There's my diagram. X and Y, from the bottom of the X all the way over to the pole is 10 meters. They drew it at the top, either way. Then you have 1 meter, 4 meters. The good news is about this 1 meter, I'm going to ignore that 1 meter and understand from the top of the light pole to the gun is 4 meters. Gives us a nice triangle. So there is our coordinate system. Take a second, make certain you have it right, make certain you have it down in your notes. Seconds over, here we go. So, easy part, you find the inverse tangent of the delta x, or delta y over delta x. Find your angle is 21 degrees, 22 roughly. So, now, we need to know an x and t system. Easiest equation, delta x equals the velocity times the angle times t. The problem is we don't have t, but we do have x. Resort it. This means the dart is actually going to fall, or excuse me, the dart's going to be shot for 0.215. Also, the banana is going to, in theory, fall for 0.215 seconds. Good news is we can find the height of the banana because we know 1/2 times acceleration due to y, or gravity, times the time gives us it's going to fall negative 0.227 meters from where it starts. The dart is a little bit harder, but we can still find it. Delta y equals vi sine of theta. So again, trying to find the velocity in just the y direction at a set time. And then understand, since you're firing it up, you've got to come back down due to gravity. So 1/2 acceleration due to gravity, or AY, times the time squared. So initially, hey, great, AY, it was aimed at 4 meters, where the monkey was. But since gravity pulls it down, it's going to fall down here. Now we have a distance of 0.227 and 3.76. First question, did she hit the monkey? No, she missed the monkey. Second, did she hit the banana? 0.227 and 0.376. I think it's going to be close. They're both 4.7 and 4.76. I would say she hit the banana with a dart. Should be pretty cool to watch, but for tranquilizing a monkey, she's a failure. It happens. All right. That is the big chunk of chapter 3 right there. Relative motion, we've kind of already talked about in class once or twice, and only because other students have brought it up. Example, if you're riding in a train and you drop an object, any object, it looks like, from your perspective, if it drops straight down, because it's above it, down. Now, for someone sitting on the outside of the train, watching the train go by, that briefcase is going to look like it's going forward. You don't notice it from your frame of reference because you are moving the same speed forward in the x direction as they are, or as the train is, as the briefcase is. Them sitting on the side do not have any velocity, can see your velocity of your train, of you, and the briefcase, all as separate things. So, frame of reference, if you're moving 80 kilometers to the north and a car passes you 90 kilometers, seems to be moving 10 kilometers more. Easy enough. So imagine you're driving down the road, someone passes you, you can figure out 10 kilometers an hour. Now, someone moving on the side of the road, that's going to seem like the faster is 90 kilometers towards the north, just because they're sitting still and you are not. Important difference. A lot of frame of reference. We'll get into this second semester as well, frame of reference with talking about physics and, more importantly, relative motion and relative velocity. All right. And we're not going to do these questions. So that should bring you up to speed. If you understood every equation, rock on. If you don't, well, don't feel bad. We're going to do quite a few of them in class to make certain you understand which section is important, which sections are not, and how to use all the calculations. As always, if you have questions, go back and look at the section of the video, then bring it up in class. We'll come up with solutions, equations, everything you need. Make certain you never leave class without understanding. As always, if you have questions, email me or see me in class. Have a good day.